I think that we are alive. Let's hope. With any luck. So, AI is going to show off the crazy world of the next several years of its life. So, this is what we call a Kanban board. So, it's basically a list of tasks that I'm going to try and get done. And this is like all the stuff I currently have planned for Stylizer, which is my stylization focused game engine, game framework thing that I'm working on. So today we're going to work on implementing some features for Quaternions. And I guess if we're going to implement some features for Quaternions, it would probably be good to talk a little bit about what a Quaternion is. So let's go ahead and do that real fast. So, what is a Quaternion? I ask as I put on my silly little glove thing. So, what's a Quaternion? Well, last time, let's pull that back. So, what's a Quaternion? Well, a Quaternion is a way of encoding a rotation. So, what do we do with one of these encoded rotations? So hi, DJ. I hope you enjoy your coffee. Well, they're a method of encoding rotation to avoid gimbal lock. So in the last video, we talked a little bit about how when you rotate, sometimes you can get two of your axes of rotations lined up. And then if you try to do animation, when animated, these look really bad. So a quaternion is an alternative means of encoding an animation that can be blended a little bit better. Why? What's the point of this over something else? Well, rotation matrices can be blended, and they're pretty good. But to encode one, you need 9 floats. Whereas with a quaternion, you only need 4 floats. And this is encoding 3 degrees of rotational freedom. So what does that mean? That means that I can rotate around X or Y or Z or whatever I want. And so a quaternion wastes 1 float. 4 minus 3 is 1, whereas a rotation matrix wastes 6 floats. 9 minus 3 is 6. So they got some use, but what are they? Well, we take an axis that we're going to rotate around. So we're going to define this as a vector x, y, z. And then we take an angle that we want to rotate around that axis. So what does this then look like? Well, the obvious thought would be that we can just write x, y, z angle. But it turns out that that doesn't work out really well. Also observation, angles involve a lot of cosine and sine, and those are expensive. So we want to avoid doing those operations as much as we possibly can. So what happens if we pre-compute sine and cosine, and then we just bake that into our representation? Which way around are they? Quaternion as compression. To compare quaternion as axis angle. Believe the sine. Yes, the sine goes inside. So what do I mean by that? Well, instead of just writing this straight, we're going to write x we're going to write x times the sine of the angle times y times the sine of the angle, then z times the sine of the angle, and then the cosine of the angle. But technically I'm lying. This will work, but for it to work properly for rotating vectors, you need to be storing angle over 2. And we should see why in a few minutes. So what about this? Well, it turns out that this representation is just a vector 4. So it turns out that Stylizer has a little bit of a math library. And if we come and take a look at it, you see that we already have definitions for vectors, including a vector 4. So all we just need is to take the existing vector 4 and add some of the Quaternion specific operations to it. So that's the goal of tonight's stream. And first I need to take this glove off because this glove is very uncomfortable to write code with. But first, I have a couple of things I want to do to vectors in general. I want to be able to apply some function to every element of a vector. And I think I already have lerp. Don't we already have vector lerp? We do not. Okay. So I want to implement those two things. So let's open up the vectors partial operations file. Then down here at the bottom, let's make an inline friend function. So a function that has access to all of the hidden fields of this class. It's going to return the same thing, so the same type of vector, and we're going to call it element-wise transform. It's going to be a template. It's going to take do we want it to be like a function? We're just gonna call it f for now. Function. And then we're going to take a t function, I guess probably by const reference would generally be best, function. And then we're going to return, I believe vectors have an array form. So we can do begin end. So let's implement this by making a new vector out. It's going to be equal to the content we have. And then we're going to say for auto reference element in out, we're going to call function on out. How does the C++ standard library do transforms? The transform, I'm wondering, do we want this to like assume that it's modifying out, or do we want it to return a new thing for out? So do we want the out equals to be inside this function or outside this function? How does std transform do that? The iterate operation is applied. The iterate operation validates. Okay, so it has a return. Do we want this function to be able to change the type of the vector? So do we want to be able to take in like a vec of ints for and have this function pop out a vec of floats for? I'm gonna lean towards no, because that complicates things, but that is something that we should consider. So we're gonna say probably not. So then we'll return this new vector that we made. Cool. So that's one thing checked off of our list. Then we want to do a lerp. And C++ has stood. Do they have stood mix? No, they have stood lerp. Okay, so that's an easy name. We're just gonna name it lerp. So out in the vector file, we're gonna add a new template function, type name t, can work on for any type and any size of vector. So we're gonna take a vec with that type and that size, and we're going to lerp it. So this means that we need const vec t n reference a, const vec t n reference b. So we take two vectors and we're going to blend them together. And then the super simple math for lerp, and we need like a float ratio. We usually call it t, like for time. I will call it t. And then the ratio, the math here is that we have a times t. I'm gonna do 1 minus t. So one implies no t. A times t, so 0 implies a. And we're gonna add that to b times t times 1 minus t. So what does this represent? Let's pull out the drawing stuff again. Ba, ba, bow, 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 bow. Let's clear this. So we have two points in space. We'll write it the way we have been. So we got A and we got B. And so a lerp is a linear lerp equals linear interpolation. And what does linear interpolation means? Well, it means that we're going to draw a line between these 2 points. And then we have this extra parameter here, t. So when t, let's do this in purple. When t equals 0, we're going to get point A. When t equals 1, we're going to get point B. Like when t equals 0.5, we're going to get some point that's halfway between A and B. And then we graduate. So like this would be a t equals 0.25, t equals 0.75, and so on. So a linear interpolation just creates a line between those 2 points. And then based on whatever we set t to, it tells us how we should blend between those 2 points. And I guess I have a GFX bot to get out of here. Mr. GFX bot, would you be so kind as to vacate the premises? Da-da-da. Let's block him. Cool. Block him, ban him, ban him. Timeout. Ban. That button. Where are the mods when you need them? So back on point to the code. It would probably be helpful if we did something with this interpolated value we just calculated. So we should return it. And then I believe that checks another box off of our to-do list. So now we need a quaternion type. So we're going to pragma once. So this file is only ever included once. And we're going to include vec.hpp so that we can have vector stuff. And then we're going to go struct. What are we going to call it? OpenGL calls them quats. Do we want to name it full quaternion? I think we probably want to name it full. And we're going to protectedly inherit from vec float 4. And this needs to go in our namespace. Namespace stood math. Do I want this to be a template on like stood floating on like floating point types? The API gets simpler if we just, let's, we can name this like basic Quaternion. And we can template it on, what is the floating point concept? Stood floating points? Yes. Stood floating point in concepts. So we'll template that on stood floating point F. And we'll put F in there. Cool. Since we protected inherited, that means that only this class and things that inherit from it can access like the fields of the vector. So there's a couple of fields that we want to expose. So we want element-wise plus, and we want scalar multiply, scalar divide. So I believe that means we can just using operate scale it super. So using super equals vec f4. So we're going to use super operator plus using super operator minus. Switch to tabs. If we just use multiply, that'll bring everything. So I think we need to make a multiply. So we're gonna have something that returns a basic quaternion operator multiply. And it takes a basic quaternion F. And since we want this to take two things, we'll make this an inline friend. Since it's a friend, it has access to all the stuff in vec, even though it's protected. And we'll do this by const reference, call that Q. And then we want an F, which we'll call scalar. So we want to be able to multiply this quaternion by F. So we're just gonna pretend that Q is a vector. And then we should be able to do the scalar multiply that's already in vector. Cool. So we want the same thing for scalar division. And I'm going to copy scalar modular. It doesn't exist for floating point types. So we don't want anything for a float. So that checks a few more boxes off of our to-do list. Standard dot product. Do I need to do anything for that? I don't think so. So we'll leave that as a question mark for now. So now I want quaternion multiplication. Welcome back, Fish. How's the coffee? Is the coffee Gouda? So quaternion multiplication. Let's pull this back out. And there's a little bit of notation here that I should explain. So earlier, we mentioned that a quaternion shoves is x cos of angle over 2, y cos of angle over 2, z, oops, not cos, sine x sine angle over 2, y sine angle over 2, z sine angle over 2, cosine of angle over 2 in the x, y, z, w slots of a vec4. You also have a baby. Is it a cute baby? Well, in a lot of the Quaternion parlance, right? They define that S is equal to W, and then V is equal to the vector X, Y, Z that we have here. So then they write the Quaternion as, instead of all this, just SV. So then let's pull up the multiplication here, right? So they have SA, SB, B. So let's slide that over here so I can look at it. So if we want to define multiplication of two quaternions, so we have A times B, that's going to be equal to SA, A, and SB, B. So these are these are XYZW, and then this, XYZ, and then these are W. We'll keep that in mind. And then multiplication is the two W's multiplied together. So SA times SB minus A dotted with B, and that will give us the S of the new quaternion. And then we have SA times B, that's scalar multiply, plus SB times A, another scalar multiply, plus A cross product with B. So, with that fun definition out of the way, let's go implement it. So let's write a inline friend basic quaternion multiply. Just going to take const basic quaternion F reference A, const basic quaternion F reference B. And so then note SA equals W, A equals A dot XYZ, A dot W. And then up here we'll also note SB equals B dot W, B equals B dot XYZ. So then multiplication is basic quaternion F. So we'll do it in two parts. We got W. So F W is going to be equal to SA is equal to, so S is equal to SA times SB minus dot of A and B. Is that how I have dot product implemented? Is it a friend? It's a friend, yeah. So dot of A and B. So SA is A dot W times B dot W minus the dot product of A dot XYZ with B dot XYZ. Babel, is that? Oh, it's the fancy cheese and wax. Oh, Baby Bell. Oh, yeah, I understand. You got fancy cheese. Yeah, it doesn't like the exact type of cheese they have in there. It's kind of meh. And then the XYZ part of the result, which the notation likes to call V, is equal to SA time multiplied by B plus SB multiplied by A plus cross AB. So we got a vec F3. V is equal to SA times B dot XYZ. Oh, SA is A dot W plus SB is B dot W times A dot XYZ. And then that's equal to the cross product of A dot XYZ and B dot XYZ. Is meh, but is snacking. I guess that's fair. It's cheap cheese too, if AI remembers correctly. Cheap cheese is good cheese. And then we should be able to return a vec F4, which we construct from V and W, which then should convert to basic quaternion. So instead of calling this V, we'll call this XYZ. Cool. So that's another box helpfully checked on our implementation list. So now we have the conjugate. The conjugate is it's like kind of hard to explain like how it's useful by itself. It's like a piece that like all the other stuff uses. But fortunately, it's pretty easy to implement. But we should probably also inline friend basic quaternion operator star so that we can just multiply things. Const basic quaternion F reference A, const basic quaternion F reference B, and that will just return multiply A and B. So we'll just make the operator overload of this multiply function. Is meh and waxy, but is snacking? Mm. Um, so inline friend, this only takes one quaternion. So I think, how have we been doing like lengths? Yeah, they're constant. So inline friend, no, not friend. So we'll just do it as a member. Basic quaternion, conjugate, and that will be consts. We don't need to change anything about ourselves in this. And we're just going to return vec f4. We're going to construct another vec4, and it's negative star this, negative xyz. They're not going to let me do that, are they? This xyz. Or I could do super xyz probably. And w. This w. Oh, I should probably be forwarding all this stuff. I wonder if we have that. We'll see. So using super X, using super Y, using super Z, using super W, using super, what was the other one called? Data. So we make sure that all of the element, actually, do we want to make sure that all the element-wise accessors are available? Do we? Whatever, we did. So we got conjugate. So that's another box off of our checklist. And then we have the normalized form, which is multiplying the quaternion by its conjugate. And then, so let's do inline basic quaternion, squared, normalized squared, const. And for this, we're just going to return star this, multiplied by the conjugate. And then inline basic quaternion normalized const. So when we normalize a quaternion, what we're doing is we're taking like the length of the vector and making sure that it has a length of 1. So like the normalized quaternions, make sure that like there's no weirdness going on with rotations. So you basically, as I understand it, always want your quaternions to be normalized. And to normalize, we need to use that new element-wise transform function that we defined. Actually, should that be a friend? That should not be a friend. We want that to just exist. So we're going to this element-wise transform. We're going to find a new function which takes an f element. And then what do we want to do to that element? I believe we want to square root that element. We check the noted down math here. Squared norm is q times the conjugate, and norm is the square root of the squared norm. Looks good. So we'll check those off of our list. I guess we could do so. No. So, I call these length other places. So we'll call this length squared. Then we'll call this length. Does squared this? Wait. Am I supposed to just take the W of this? Quaternions unnormalized. Normalization. Da. There's a nice article on quaternions. Do I have it linked somewhere still? Searching my notes. Quaternion. Understanding quaternions. Is this it? Yo, Finch, can you remind AI that this link needs to go in the description of this video? And I should on here pin that in my notes. So this article does an explanation of what quaternions do a bit better than like the blitz overview that I'm doing. It goes into like why you do all these things. So similarly, the norm of a quaternion is defined as actually, okay, so we already have length and length squared. Because, yeah, so we already have length. We don't need a function for length. We just need to using super. We have squared length. Yeah, length squared. Using super squared length, using super length. Which seem like they should work based on this definition, since that's just Pythagorean theorem for length. Link in description. Thank you, Fish. Cool. So I guess that's two easy checkboxes. So then we want the normalized, which I think is also the same. I believe we have a freestanding normalize. Yeah. Do I need to write one? To do will the existing freestanding normalize what? I should probably using super's constructor so we can construct it from vectors and stuff. So I have support for that in here. So normalize. Then the inverse is the conjugate divided by the norm. So inline basic Quaternion inverse const. And let's return the conjugate divided by the length. There's a square root in length, so this is kind of an expensive operation. And then we have vector multiply. So inline friend vec. Let's actually make this a 10. Nah, we'll force it to use f. So vec f3. And we want the quaternion. I actually kind of want this to go either way. So we'll write the either way version for this. So actually, is that true? Or do these only to do is it should be. It should be. Yeah, we'll make it be either way around. So vector multiply. So we need a const basic quaternion f reference a. I need a vector 3 const reference b. Cool. So the idea here is that this is actually, I'm not call it vector rotate. We're going to call it multiply. We're going to call it rotate vector. That's a little bit more logical of a name, because what this function does is it uses the quaternion to rotate the vector. So we're actually doing the rotation part now. And to do that, we take auto conj equals a dot conjugate. And then we take auto, what are we going to call it? B quat is equal to the quaternion B 0. So 0v is equal to that. So we're just going to do some quaternion multiplies now. I suspect that there's probably a better way to do this. To do, is there a more efficient way to write this? But that is not my concern at the moment. Make it good, and then make it exist, and then you can make it good. So, actually, we're gonna call instead of A, we're gonna call this Q. We're gonna call this V. Then we're gonna call this Q, V, V quat. Then we got some multiplying. So we got Q times V quat, and then that result we're going to multiply. Let's not store it in a variable. By V conj. And then this is going to go into auto outquat. And then we return outquat dot xyz. So we just drop off the W. So that's vector multiplying. So an angular difference. So we got quaternion, the dot product of quaternion 1 with quaternion 2. Then we divide that by their lengths multiplied. Cool. So what are we going to call this? We're going to call this inline friend. And this is probably a radian. Angle 2. Const basic quaternion f reference. The reference should not be on the inside there. A const basic quaternion f. Oh, should this be a property? So I'm calling it angle 2, we'll call it angle between. Reference bing. So this is dot a bing divided by a dot length divided by b dot length. Cool. And I think normally these types of things come out in radians, so I'm going to assume that this comes out in radians. To do, does this produce a value in radians? It probably does. So then we have the Euler axis. of the angle axis. So let's implement angle axis functions. So for starters, we'll do it. I don't know where we'll do it. We'll do it down here for now. Then we might move it. So we got a static, basic quaternion from angle axis. So we got a const back radian 3. No. F3 axis, and then we got a radian angle. So we talked about the formula here earlier. So we're gonna pre-compute the angle. So we're gonna say radian auto s equals sine of angle, auto c equals cosine of the angle. And we'll make sure that we're using our version, stud math. And then we return, what is this? So we're going to return a vec f4, which you're going to construct from axis.x times sine, axis.y times sine, axis.z times sine, and then c. So I guess we can just shove the cosine version in here since we only use it once. And then we need we're gonna return this stud pair back f3 radian 2 angle axis. Let's do this 2 ways. We're gonna have a void function which takes a vec f3 axis reference. So we're gonna return it through the parameters and a radian reference angle. We're gonna add a little note here, out parameter, and we're gonna add a little note here, out parameter. How do we do this computation? Two from axis angle. So the from version, no, the to version, we have to undo this. So we can get the angle, which is equal to cos inverse of W. And then from that, we can get sine of angle, which is going, so we can get S, which will be equal to sine of angle. And then we have XYZW is equal to, so then axis is equal to XYZ divided by S. So let's write that. So angle, actually, that's basically just the code. We substitute this like so. And then XYZW is a function. And we can divide sine the angle. So we can divide off the angle. That I think does it. Then we can have stood pair of vec F3 and a radian. Two axis, two angle, no. Angle axis, axis angle. Call it angle axis. Angle axis. For calling it that, we should probably have the angle be the first parameter then. Let's just call it axis angle. I'm used to other things calling it axis angle, so I think that's the more agreed upon axis angle. It's the more agreed upon border. And this will just return stood pair of this, which we're going to call out. Then we're going to two axis angle out dot first, out dot second, and we return out. Cool. Now we have the Euler axis version. That's gonna take a while. So instead of doing that, let's go write some tests. Make sure that all the code we just wrote works. So we're gonna, it already brought in angles.hpp. Cool. So let's make some new tests. Well, first off, let's make sure that our current tests work. There's a problem. Tightening T function. It's a problem with element-wise transform. Cool. So let's make sure that our current tests work. They do. So let's make a new test. Quaternion. And since we named it full, we're going to call this Quaternion. Quaternion.hpp. Quaternion.cpp. We'll add it to the test list. Quaternion.cpp. Does nothing. Cool. So let's add a test case. We want to include doc test for testing. And we want to include math/quaternion.hpp. So we have a test case. What are we testing? Quaternion. Quaternion. Quaternion basics. So we want to do addition, subtraction. So we're going to do Quaternion. We'll add an override in here. We'll say that thing using Quaternion. The canonical Quaternion is a basic Quaternion on stood float 32_t. And we want that after this question. That question should come before. So, stood math. Quaternion. A is going to be, actually, yeah, so we're going to do 1, 2, 3, 4. And then B is going to be 5, 6, 7, 8. And so now let's go A. So we're going to check that A plus B is equal to Stud Math Quaternion 6, 8, 10, 12. Okay. How do we feel about all that? The 30 was not declared in this scope. Yes, I think I did mean stud float 32. Instantiation of struct operator plus has not been declared. Yeah, it has. Operator. Oh no, they're friends. Okay, does that mean? It's not a question. Does that mean it just works? No, we need to specify that they'll work. So we need inline friend, basic quaternion, operator plus const basic quaternion reference A, const basic quaternion reference B, return super reference A plus super reference B. Cool. Then we'll do the same thing for minus. We need to do that. Not convert. So we probably need to wrap that in a conversion. They're in conversion. This is fine. So I think it's upset that because we can't use relational operators. So we'll do the same thing for the relational operators. So equals. Not equals. Less equals. Greater equals. And then less than and greater than. Instantiation of plus. Warning, don't care. And instantiation error. Okay, so let's pull this out of the doc test stuff so we get less of the doc set test. BS. I think these have to be initializer list version then. They're in conversion. That's fine. instantiation of no matching function. Are you complaining that I have to do this? Do I have to do an order precedence thing here? No matching function for called all of. Why are we calling all of? What? So a plus b is correctly using the plus function. Let's go look at the plus function. So operator bool. What? Instead of super reference, let's do super A. Super B, see what that does. Why are we getting a bool? Yes, we got vec float 32 4. Why are we operator booling? Okay, so let's drop the protected function real fast. Super reference as super. So we're gonna return star this. Now we can go a dot as super. B dot as super. Let's see. There's still a narrowing conversion happening. And that can be const. We're not changing anything about ourselves. Const super reference. We still have a narrowing conversion. So let's add. Let's name all of these. So we're gonna call this add. Then we're gonna go in line friend operator plus return add AB. call this subtract. Subtract. We'll call this negate. We'll copy the same condition. Operator minus. Turn negate A. Call this multiply. And we'll just, guess we'll do both versions. Second version needs the template. Then we return multiply AB. We call these operator star. We call these divide. Do the same thing. Turn, divide, AB. Call this operator slash. Do the same thing. Modulus. There we go. Grab the conditions on these. Return modulus AB. I'm not going to worry about not in friends at the moment. So now in here, Quaternion, we're going to add A.S super plus B.S super. Are we still narrowing? Oh, we should probably returning that. So what doesn't it like? T-like does not name a type. I lost a template here. Error conversion. Why do we have this spool happening? So we're going to comment out all of these except equal. So inline friend, basic quaternion add, const basic quaternion reference A, const basic quaternion reference B. I'm going to add underscores to those names. Auto A equals A underscore dot S super. Auto B equals B underscore dot S super. Return add A B. The fact that this is a reference that's throwing things off. This needs to be const. No, it doesn't. Let's add a version of this which is not const. I compiled. So why does that compile but this doesn't compile? It's probably the type materialization. We can specify. Does that compile? No. Is it an accessible base? So we inline friend basic quaternion operator plus basic quaternion. Pull those references over the way I prefer them. Return. Add AB. Cool. Now is it happy? Cannot convert studmath add. From a vector 4 to a quaternion. Narrowing conversion. Okay, let's add a helper. Static basic quaternion from vec 4 const vec f4 reference v return v.x v.y v.z v.w. So we'll do a copy there from vec 4. It's no longer narrowing, so it's no longer upset. So now if we simplify this to dot as super, get rid of the underscores. Are we happy now? We are happy now. But this doesn't have an arrowing conversion. Well, it also doesn't return a basic quaternion. These all return vec for bools. Vec bool boors. In template redefinition of modulus. Okay. So let's try copying these down. And since we have the fancy as super thing, let's use it instead of these. Oh, hello! It's a Guiar. Is that how you pronounce your name? How are you doing? As super. Are we happy now, do you think? Will it explode? Guys, it's alive. You're doing good? Well, I'm happy to hear that you're doing good. How am I? I'm alive. I'm sleepy. I'm dealing with implicit conversion to Boolean hell. It's my favorite type of hell to be in. So test compiles. Test should compile with proper order of operations too. Yes. But now we want to check all of these. Are you happy now? Did you break? Are we on fire? Yay! All of the tests passed! Can you believe it, guys? It's working! Yeah, I'm so happy. Uh, Greer, how long is the stream delay on the YouTube side? I wrote a little. Oh, not long. If you're responding to cool, that's a reasonable amount of latency for interactivity. I did a bunch of code, but what is working? What is working? 87 minutes? No, not 87 minutes. We have an ad. The ad function is working. The simplest thing I could possibly have gotten working is working. I guess I should probably do a little spiel about what we're doing today. So this is my Kanban board, my to-do list of things to do for Stylizer, which is what I'm calling my stylization focused game framework engine thingy. So we're going through the top thing on the list, which is to implement quaternions. And quaternions are a method of storing rotations. So we have addition working and tested. And I'm willing to bet that with like a quick copy paste, we'll have subtraction working and tested. So let's check all of a minus b is equal to 1 minus 5 is -4. 2 minus 6 is -4. 3 minus 7 is -4. I'm noticing a pattern here. You should tell me that you know absolutely zero things about coding and game dev. Well, you found my channel, which is the correct place to be if you're in that situation. Oh, where are the shorts and stuff being out? I don't. Nah, none of the rotation shorts are anywhere near being out. But actually, the math video isn't out either, is it? The math video comes out tomorrow. That was bad timing on my part. I should have done the stream tomorrow. I can't just tell someone to go watch the math video because the math video doesn't exist yet. Maybe the YouTube gods pointed you here? Well, if they did, I appreciate it. What is happening? Let's describe what's happening here. Give you a little bit of spoiler for the video that comes out tomorrow. Hello? Laptop? Would you like to come alive? Thank you. So, math jump scare? Well, I'm sorry. It is what it has to be. We are hosting. Dismiss session. Join. Cool. So, the problem that we want to solve is, say we have some 3D model. And obviously, if every 3D model is a cube, because that's like the only thing I'm good enough to draw. Well, now we want it to be rotated. A little bit. So maybe something like this. Well, how do we define that rotation? Well, we can figure out what axis we need to rotate around, and we need to figure out how much we need to rotate around that axis, right? To go from like this slanted cube to this more straight cube. Then we can encode that information into a quaternion. There's a lot of other ways to encode him, but this one is really good for animation and avoiding waste. Those are the two main things that quaternions are good at. We also got like rotation matrices, which are good at animation, but they're very wasteful. And we got Euler angles. And we got some other stuff. I explain all of these in the video that came out tomorrow, so don't worry about them. They're not important. The moral of the story is that we're defining a way to do rotations around some axis and doing it efficiently. That's the thing that's happening right now. And I just spewed out a bunch of the code to make it happen. And now we're testing all that code to make sure it works. And so far, we know that adding and subtracting two quaternions works. We also know that equals works, so I'm going to assume that these all work. So I am doing an engine. Yep. The goal here, there's an interesting, yes and no. Engine is too strong of a word for what's being created here. There's like a sliding line. Yes, I guess we're gonna pull the drawing stuff back out. There's like a sliding line between what we call, well, actually, there's like a triangle. So we got game engines. Nah. Game engines, frameworks. Nah, it's a line, not a triangle. So we got game engines. Oh, we'll actually write it like this. So you can do everything. I like how I proceeded to take the glove off as I was about to do some drawing. Then everything went to hell. So you can do everything yourself. I'm making it hard to work. No, you're good. I'm actually very happy. This is like the first time someone has popped in and asked me about what I'm doing, so I appreciate your presence. Then, at the far end of the spectrum, there's a game engine. And a game engine does a lot for you. So usually game engines have stuff like physics. They have stuff for like creating scenes. They have like an editor. Like Unreal or something like that. Source 2, exactly. And then like halfway between, there's a game framework. So this is like a spectrum, right? From do-it-yourself to a game engine. And like game framework sits somewhere in the middle. And a game framework gives you simpler things. Like it does some graphics for you, usually does sound, usually does some input. And game engines also tend to be a little bit opinionated. So like they have like an architecture. So like Unity has their tree, their tree with components. Their Unity has their components. Like Godot has a scene tree. So there's some architecture that the engine usually puts on you. The other one, Bevy, has ECS, Entity Component Systems. Whereas the game framework is just kind of like, okay, here's some functions to draw stuff on the screen, you figure it out, if that makes sense. Here's some functions to play a sound, you figure it out. So the game engine has like more structure. Has ECS, is ECS. How do you talk about that? Bevy. I think either one works. Bevy has the ECS architecture, and Bevy also implements. Bevy is an ECS data structure. So I think either way of phrasing it is correct. Godot's an engine. Godot is like very similar to Unity. It's just free. How do I test? Well, we can do scalar multiplication. Testing scalar multiplication is easy. So this is elements wise operations. This is scalar operations. We have since we have the new function I made. Oh, I guess we only used it here. Cool. So q.as super, q.as super. Convert tabs to white space. So let's multiply it by 5. So that should give us 5, 10, 15, 20. And let's divide it by 2, which should give us 1/2. Ooh, how do I test division? Let's divide it by 1/2. Which should give us 5, 10, 15, 20. Spectrum example is, am I on Twitch too? I am in fact on Twitch too. I don't know if you noticed that DJ, if he can pop in, when he sends messages, he'll have the little Twitch logo and his name. You're not missing anything. Well, I'm doing this. You do dungeon? What the heck does that mean? Are you putting horse girls in a dungeon? Put the link in. I don't know, man. You're not missing anything. I do. What's the word? I have Creative Commons in my head, but We're gonna say labor of love. I do labor of love, so I haven't, like, done any of the stuff to, like, that Twitch give me money, which by extension means that, like, Twitch doesn't have any of the fun stuff. So I believe YouTube actually probably has the better viewing experience. Um, one of these years I'll get a bot. I'm willing to bet that the divide by 1/2 is gonna break everything. Ambiguous overload for operator star. Okay. Just want to drop a follow? YouTube is better? Well, if you just want to drop a follow, I would appreciate that. TV/sleepy doxy. There you go. Yo, I like how the link just disappeared from the viewer. I love finding new bugs to fix. It's my favorite recreational activity. ISO C++ says these are ambiguous, even though the worst conversion of the first is better. Is that an error? There is an error here. Okay, so let's get rid of the doc test shenanigans. You're welcome. Oh. That's why it's Anki. These need to be templated on a T-like. So template T-like. Call it F-like actually. Template it on F-like. Oh, but that's gonna be ambiguous now again, isn't it? Cannot convert. You telling me that you want multiply? And if that's correct, then I'm going to assume that down here is going to tell me that it wants divide. Oh, not multiply from vector for self. Oh. From back 4 is what's complaining. Oh! Is that the complaint here? So does this actually work? It's just complaining that it... Ah! Okay, that makes sense. And so we're going to want to from back 4 on multiply. We're going to want to from back 4 on this. We're going to want from back 4 on this. Well, so we're compiling now. So let's check if it's correct. Yang! Which hopefully means that division is correct. No one find what? Oh, we're not doing Horse Girls, we're doing Final Fantasies. I see. Can it do the bool conversion thing now? Not that it can actually print what we're getting. So let's do this a little debug and see what we're actually getting. I'm guessing that this is just floating point error. Should I make an approx? I should make an approx equal for vector probably. What did I call it for floats? I called it float equal. I don't like that name. Call it approximately equal. So now let's go into vec and we'll do approximately equal template type 18 size tn. So we want a vector const vec tn 8 reference a const vec tn reference p. So we want to check if these two vectors are approximately equal. So we're going to go for size ti is 0, I is less than n. So we're going to loop over n times plus I. And then if not approximately equal a dot data I and b dot data I, then we're going to return false. So as we loop over, if any pair are not approximately equal, then the whole thing can't be approximately equal. And then if none of them aren't approximately equal, that means the whole thing is approximately equal. Did that break the tests, or did they update names? That broke the tests. Approximately equal. So let's update that in all the places it's used. Approximately equal. Are there any issues? Are we failing? Vec.cpp also has approximately equal. Approximately equal. So the issue here is that the way a computer stores decimal numbers is not intuitive. Like there's a bunch of numbers that can't be stored. The most obvious one is 0.3. So like if you look at 0.3, what it actually equals is like 0.3000021. And like this little 21 means that like numbers involving decimal points are never equal in computers. So we have to check if they're equal, but like within a small margin of each other. So it's a property of binary because we store the decimal point as either 0 and 1, right? So we have the 2's place, the 1/2's place, the 1/4's place, the 1/8's place, etc. And either there isn't as a 1/2, there is not a 1/2, there is a 1/4, there is not a 1/8, right? So if things fall nicely into one of the divisible by 2 ranges, it works. What do you notice about 0.3, which is 1/3? Well, it's not falling nicely in the 1/2's place or the 1/4's place. So you end up needing to make like 1/2 plus something a little bit, like a bunch of really small things to add up really close to 0.3. But you can't since we have a finite amount of space to store these numbers, we can't ever get exactly 0.3, if that makes sense. That worked. So Quaternion. So instead of equal, we'll do stood math approximately equal. Yep. Much smaller number, and actually quite a few of them. Because you need like quite a few numbers to add up the 1/2. So it's actually going to be like 1/2 and like 1/16 and 1/32 or something. I don't know exactly what it is off the top of my head. I wish that you would be aware that float 64 is in fact is inaccessible. Fudge. So let's make. Where is Vec? Do I care about? Oh, I would like. Do I want? I would like normalize, and I would like approximately equal. So does the existing freestanding normalize work? Based on this, I'm guessing the answer is no. So let's implement one. This will be basic Quaternion F, and then we can change this to being template on F, template on F, and we know that this is always for and b divided by length will hopefully work. I pray. But the test, the approximately equal, is now compiling. And actually, we should be able to return. Actually, if we put these inside the class, like up here as friends. I wonder if you can have a context per friend if it'll get mad. We should be able to return normalize as super. We'll call this Q. Q dot as super. And we don't need to template it anymore since we can inherit the template of the class. Then we should be able to return approximately equal A dot as super and B dot as super. Cool. Or not. I guess we can not do that too. That also works, I guess. So much for my life being easy. Well, but actually, if we just prototype them in here as friends. That should work. Maybe. Did you pray to the machine god? No, my computer mana is not high enough for tonight's stream. when declaration declares a non-template function. Uh, templates, type name, F2. And we'll type these on F2 then. Cool. And now it should be Angie. So we should comment that out. Return, normalize, q dot as super. And then we're gonna need basic quaternion f, run back 4. And then we're gonna need here approximately equal a dot as super and b dot as super. I have not sufficiently praised the Omnisaya yet. And now let's check if they're approximately equal. And fingers crossed. I hate everything. Well, so let's divide by 2. We'll check. What is that? 1/2, 1, 3/2, 2. Okay, what numbers am I actually getting in? Are approximately equal? I said, what numbers am I actually getting in? Try applying the oils. We'll get right on that. So what is A store? 0.51, 1.52. And we're getting back false. What are we getting for the other one? This is probably, okay. I am now of the opinion that this is telling me that my epsilon is too small. So we got, oh, B is just wrong. Why is B just wrong? Oh, because these are integers. That dungeon sucked. What happened? Thank you for coming to your TED Talk, but your TED Talk didn't tell me any information. I'd like to argue that this is a pretty shitty TED Talk. Double. We'll make them floats. Are you happy now? You are happy now. Yay. Yang! It's just because I'm an idiot. Woohoo! Well, they informed us that the dungeon in fact sucked. That is definitely an informationalization. Lots of annoying mechanics in the fight. My party wiped 4 times and the healer kept going down first. Well, guard your healer better, 5-head. So now we need to test Quaternion multiplication. So we're gonna do A times B I don't. So we're gonna leave this as a to-do. To-do, come up with a quat mult test. So we can do conjugate. So conjugate. So check. A dot conjugate equals what would this be? This should be -1, -2, -3, 4. I think. No match for operator minus because we can't use. Where's conjugate? We can't have a good time. So instead we gotta negate it. Hey, look, it's a Russell. Hi, Russell. How are you doing? Took damage from it and had to pop my invulnerability, and I healed him after every big AoE, but I ran out of juice to heal him. Wait, but. Get a better healer. Class template argument deduction. No, it doesn't like the swizzle. So we need to manually .as Beckett. Did I mean Tuvek? I did mean Tuvek. Oh. Does Tuvek? Let's go look at the swizzles. Does Tuvek not have so we got swizzle operators. We in fact do not have a const version. So let's make a const version. And that then means down here at the bottom, I believe. I'll need to make a const version. I'll need to make a const version. I'll need to make a const version. Maybe get rid of the extra space to make. Maybe get rid of the other extra space. Need to make a const version. Also, because I've been fighting the boss since you mentioned it, I never understood anything you're doing here. AI has shorts, and AI appreciate. Like my YouTube channel is just shorts, basically explaining what I'm doing here. We're not all the way through though, so I can't fully say that. We failed again? Why we fail again? On XYZ equals this XYZ to vec, XYZ. We materialize it, will it be happier? Nope. Stud math negate, maybe? Is negate... Negate is a friend. Negate should probably not be a friend. And then if negate's not a friend, then we can that 2vec.negate. Okay. Oh, and if it's not a friend, I should no longer take A, and should be this dot to SIMD. That doesn't mean I understand how you teach it. That's fair. And negate. Oh shoot! Does the const go here? Vec3 float is ambiguous. Auto XYZ. XYZ dot X, XY, XYZ dot Y, XYZ dot Z, this W. Really? In the const version? Really, do I have to const? Ay, ay, ay. King. So in the const version, we'll T-pointer cast in, I guess. So we'll cast off the const. See if that makes it happen. Partials. Run. Swizzle. How does that look? Oh, that made it happy. What is it correct? It is correct. Yay! Okay. Okay, we're almost done. So let's try from angle axis. So we'll do auto. Actually, we'll do A equals from angle axis. What are we doing for angles? Actually do vec Stood math degree. Please don't swizzle your nizzles, Russell. That's bad. 45, 0, 0. So we'll do a 45-degree rotation around the X. Let's see how upset it is about this. Oh, it wants a stood math thing. And it wants a stood math Quaternion there. Okay, I'm listening. I'm hearing you out. Russell swizzles your nizzle. Well, I mean, I can't stop you, but I don't have to like it. Don't I have conversion from other types implemented? I could have sworn I did. Is it explicit? Know that you're being judged? Yeah, you get it. I don't have. I could have sworn I had vector-vector conversions. Constructors not partial? Yeah, I do have vector-vector conversions. Okay, so let's do auto. So stead math. Yo, it's the string. Radian of back radian 3 r is equal to the degree 1. And we'll do from angle r. Oh, mayhaps stood math radian might be a good thing. Oh, was that the problem? Is that what I didn't mention last time? Oh. I'm an idiot. I'm doing Euler. So I need an axis. So we're gonna rotate back. So stood math, back 3, back float 3. So we're gonna rotate around the x-axis by stood math degree 25. And it's exploding. Oh, probably because I need to be multiplying by s in here instead of sine. Well, I guess we can call it sine since we quantified the function name. Why is it inking? Oh. No math. Tell me I have to cast all of them to Fs? Static cast F. This junk. 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 Cool. It's beautiful. Doesn't work. What are we getting out here? What is the value of A now? Let's go over to our tests. Gotta make some popcorn. See you later. Bye, Guar. And that's tall cheetah man running you over? Oh, is... Oh. It's working. It's working. Everything's working, guys. Pull out this test we don't need anymore. Debug. What's the value of A? Yo, 0.7, 0.7? That seems like something reasonable. Hey guys, we're doing it. We did it. Yatta! So now let's check the A. Stood math approximately equal A thing to 0.700, actually 0.71. 0.71. We want it to be accurate to within 0.01. Will that compile? We'll do the stood math quaternion. And we'll throw some F's on here. Make the types all match. What? Well, my brain hurts. We've been here for 2.5 hours. We're gonna call it a night. It's also, I'm also late. So we're gonna super call it a night. We're gonna disappear. We're not even gonna raid. We're just gonna